Say, okay, so given these two molecules here, I want you to look at these structures and try to see if you can't tell me which one of these two molecules would be considered more stable. All right, if they have any resonance associated with them, tell me what category that is. And then finally, you should be able to draw the resonance contributors, including those electron pushing arrows. All right, so which one's more stable, the one on the left or the one on the right? Right, why? Because it's got resonance, right? Molecules do not like to have charges. Both of these oxygens are kind of mad. They got this formal charge associated with them. But what makes it more palatable for the molecule on the right is that it can spread that negative charge out to both of those oxygens through resonance, right? So resonance helps stabilize charge. Okay, so yes. So in terms of which one is more stable, this one has no resonance. This one has resonance, which implies it's more stable. Okay, and so we established that it had resonance, right? So what category would this one belong to? Which pattern do we spy that lets us know that indeed there is resonance? So this is a pi bond between two atoms of differing electronegativity. Okay? There's also another resonance structure here, that our resonance form here, that's actually going to be more important for this particular molecule. Right? Because if we do that one, so let's do that. This comes up here. This would be our pi bond between atoms of differing electronegativity. This is a far less stable resonance contributor here, right? It's got a lot of charge separate. There's a lot of formal charge going on here. So this would not be a very stable resonance contributor, okay? Does anybody see the other type of resonance that this has available? Allylic lone pair, absolutely, right? So we have in this position, this would be the allylic position. It is allylic to that double bond. There is a lone pair in that position. So allylic lone pair, okay? And importantly, if I draw my other resonance contributor here, we can see that it's basically the exact same as my original molecule, where I have one oxygen that's single bonded with a negative charge and another oxygen that's double bonded with zero formal charge. All right, so these are two equally stable resonance contributors, so this is going to be our preferred resonance structures here. All right, where that negative charge is stabilized by spreading it out over both of those oxygens. Right? Notice how the negative charge is sitting on a different oxygen in each one of those contributors, right? Again, resonance will stabilize that charge by spreading them out. And there's my electron pushing arrows. I have one pair of electrons coming down to form a new double bond, and then I have a bond breaking arrow as well. Cool. All right, so now we're going to talk about acid-base reactions. Okay, I like this chapter because I think it's a good, easy set of reactions that has you practicing everything we've learned up until this point. Drawing your structures, drawing these arrows, interpreting those structures, as well as there's going to be a little bit of resonance mixed in here as well. Everybody's heard of acid-base reactions before. There was something that you would have studied in 1B, so we're just going to kind of put a new spin on it here. Okay? Not only that, but they are like the most important reactions spanning all disciplines of chemistry, biochemistry. There are just acid-base reactions going on all the time. All right? So, just some definitions here. An acid is a hydrogen ion donor. Okay, and we don't really call this thing a hydrogen ion. We more simply refer to it as a proton. So we say that acids are proton donors. Okay, so let's just think real quick. Hydrogen, very first element on the periodic table. If I'm holding a single hydrogen atom in my hand, it's got one proton and how many electrons if it's neutral? One. What happens if I take that electron away? What am I left with? Just a proton, right? So that's why we call hydrogen ions protons, because as soon as we take that electron and kick it away, all we're left with is that proton, okay? A base is then the exact opposite. It's a hydrogen ion acceptor, which again we refer to as a proton acceptor. Okay? So what we're going to see over and over again in these acid-base reactions is one molecule's losing a hydrogen ion, the other molecule's gaining a hydrogen ion. All right? So let's just look at a simple acid-base reaction here. We'll do HCl and hydroxide. This is one that we already took a little bit of a closer look at with our electron pushing arrows. Okay? My acid is which molecule?
HCl.
The HCl. The other molecule is my base. Okay, so again, my acid is going to lose at hydrogen ion. So now it's going to become just a chloride ion. I'm gonna run out of room. Okay. The acid becomes what we call the conjugate base. So in this reaction here, my chloride ion is what's called the conjugate base. My base is the one that accepts a proton. So my other product here will be water. And the base becomes what we call the conjugate acid. Does anybody know where these terms come from? Like, why does the acid become the conjugate base and the base become the conjugate acid? Does anybody know? Okay, it's because if you looked at the reaction in the other direction, you would see that the water is playing the role of the acid. The water is playing the role of the proton donor, and the chloride is playing the role of the base. The chloride is then accepting that proton. Right? So the whole idea is the acid becomes the conjugate base and the base becomes the conjugate acid. Where do those acid-base terms come from? From looking at the reaction in the other direction. Okay? And that's going to be something that you want to do. I know you learned about this in Chem B, how at first we started talking about chemical reactions and you only ever looked at them in one direction, and then you realized, okay, that was a little bit of a lie. We have to look at our whole thing in equilibrium and all that jazz. That's going to kind of come back in this chapter as well. We're going to learn how to predict which direction this reaction will proceed. Okay, cool. So anyway, terminology. So first thing we want to do is to be able to, like, if I give you an acid, something like, we'll just use water here. Okay, I want you to be able to tell me what the conjugate base is. What we call conjugate pairs here. Given an acid, give me the formula for the conjugate base, and then we're going to play the other game, right? Given a base, give me the formula for the conjugate acid. Okay, this is an important sort of first step and one that I think you guys have practiced before, but this is going to be an important first step because this will allow us to predict the products of our acid-base reactions. Okay, so what is my conjugate base here? If water is my acid, what would the conjugate base be? That hydroxide. Okay, so notice how we're going to go about getting our conjugate base here. All right, if we want to sort of give ourselves some simple rules here, we're going to remove a hydrogen and decrease the charge by 1. All right, so I went from a neutral water molecule to a negatively charged hydroxide molecule. Okay, so what about this ammonium ion here? Everybody take a second. Draw me the formula, draw me the structure of my conjugate base here. What's going to be the net charge on my conjugate base? 0, because I got to decrease my charge. Okay, so now I have gotten rid of a hydrogen, and now there's a lone pair on that nitrogen. Okay, and that's something we know from our rules about formal charges of nitrogen. When they're neutral, they have 3 bonds and 1 lone pair. The other thing to note here is we can now, looking at this acid-base reaction, do something that we couldn't do before, which is draw in those electron pushing arrows. Okay, everybody take a second and draw in my electron pushing arrows on my reactant side here that lead to these products. Okay, so I have a new bond being formed between oxygen and hydrogen. So my base of my arrow is going to start at that pair of electrons on the hydroxide ion. So that's my new bond. And then I'm going to break that oxygen-chlorine bond. Okay, so importantly, this pair of electrons that used to be in my hydrogen whatever bond in my acid is now a lone pair on my conjugate base. And that's what we see over here as well, right? So we said the charge decreases by 1. Why is that? Because this bond, this used to be, in this case, an oxygen-hydrogen bond, is now a lone pair. I guess I can do it on the other side. Is now a lone pair on my conjugate base. All right, same thing with our ammonium molecule here, our ion here. This bonding pair of electrons is now a lone pair on that nitrogen. Okay. So then one more for me here. Let's do... Here's my acid. Okay, draw me my conjugate base here. All right, so now we have our oxygen, but that hydrogen is off and it has that extra lone pair, right? Because this bonding pair of electrons is now a lone pair in my conjugate base. Okay, so now let's do the other conjugate pair here. So now I'm going to give you a base, and you're going to draw me its conjugate acid. right, so we got 3 molecules here. Everybody take a second and draw me the conjugate acid for each of these. All right, so when we get our conjugate acids, we're going to add a hydrogen, and we're going to increase the charge by 1. All right, so my conjugate acid for ammonia is that ammonium ion. All right, I've added another nitrogen-hydrogen bond, and what's the charge going to be? Plus, okay? And similar, what we want to note, going back to our example here, and again, what we're going to see over and over and over again, is your base is always going to have this lone pair of electrons that when it accepts that proton is now that new base hydrogen bond. Right? So we lost a lone pair going from one side to the other because it became a bond. My nitrogen lone pair became that new nitrogen-hydrogen bond. Right? Likewise, water. I'm going to now add a hydrogen. Giving it 3 bonds and 1 lone pair, so it has that net positive charge. And again, that lone pair of electrons on that oxygen is now that new oxygen-hydrogen bond. Okay? And likewise, my bromide ion, whoops, what's my conjugate acid going to be? HBr, right? Hydrobromic acid. HBr. Okay? Now, one thing that I really want to hammer home for y'all, like if you look in the stockroom in the back, you'll see we have this like special cabinet where we keep our acids and a special cabinet where we keep our bases. There are some molecules like HBr that we just classify as an acid because that's what it's used for, okay? But when we're talking about acid-base reactions, we're really talking about something playing the role of a proton donor or a proton acceptor. Notice how water was on both of our lists here. Water can play the role of an acid, or it can play the role of the base, depending on whether it's donating a proton or accepting a proton. There are many molecules like that, right, that can play the role of an acid or play the role of a base. So I guess we want to kind of have these things tangled out in your mind. We do have molecules that we consider to be acids, but in the context of acid-base reactions, we're really talking about a role, right? What's donating a proton, what's accepting a proton. For the beginning lecture here, I'm going to tell you what the acid is and what the base is, okay? And by the end of this week, we're going to have what's called a pKa table, and you're going to be able to figure out that information on your own, all right? Cool. So now let's talk about like good acids versus crap acids, okay? Bromide, we just saw, played the role of a base here. Does bromide actually play the... No, bromide is a terrible, terrible base, right? So there are some molecules that are great acids and other molecules that are crap acids. There are some molecules that are good bases and some that are crap bases, right? So let's try to tangle these out here, okay? We're going to focus specifically on acids for now. And we are then going to see that this also applies to bases in kind of an inverse way, okay? So acid strength. All right, so what is it that makes a good acid? All right, a good acid, a molecule that is very good at donating protons. It's good at donating protons because its conjugate base is super duper stable. Okay, so every strong acid has this feature where its conjugate base is a very, very stable molecule. That's how it's able to donate that proton, right? So what makes a good acid is a super stable conjugate base. Okay? One of the strongest acids that exist would be hydroiodic acid. Super duper strong. Why? Because its conjugate base, the iodide ion, is super stable. This thing is more than happy, right? We said molecules don't like having formal charges. Iodide, being all huge and electronegative, is more than happy to have that extra negative charge. The iodide ion is super, super stable. That's what makes hydroiodic acid so strong, all right? So whenever we're talking about the strength of acid, really in our minds, we want to kind of remember we're really talking about the stability of the conjugate base, right? So again, what makes this acid super strong? It's got a super stable conjugate base. What's up?
So, for strength-wise, would resonance affect that too?
This one actually doesn't have resonance. It's just a single ion. We're going to learn kind of like a set of principles that lead to stability here. And we'll see why this one is something that's so stable. Okay? So, but before we move on, let's just see intuitively here. I'm going to draw two acids. And I want you to tell me which one is the stronger of the two acids. Stronger acid. All right, and to compare them, what are you going to look at? Right? When we're saying what's a stronger acid, what is it that we really should be looking at? It's conjugate base. So let's look at the conjugate base of these two acids and see if we can't determine which one would be more stable. All right, so move this problem so I have more room. All right, so here's my acid. I really want to look at the conjugate base. So this would be, now my oxygen's been deprotonated, is what we call it when an atom loses its hydrogen. It's been deprotonated, it's lost a proton. And now I'm going to look at the conjugate base of my other molecule. Okay? And so, again, we're going to ask ourselves, which one is more stable? This actually goes back to this review that we did at the very beginning. We established that the one on the right was more stable, right, because of resonance. And that implies then that its acid is stronger, right? The more stable the conjugate base, this one's more stable. This one's less stable. So that implies this is my stronger acid. Right? When something donates a proton, as we saw, it has to accept that lone pair of electrons. Again, molecules don't really like having formal charges. What makes that sort of thing palatable is being able to spread it out through resonance, right? So my resonance stabilized conjugate base means that my acid is stronger. All right, so resonance is going to be a factor. There's going to be some other ones that we learn about as well. Okay, so let's just make a list here. Factors. That affect, hopefully with an A, acid strength, okay, but really when I'm saying acid strength, that's really code for what? The conjugate base stability, right? So acid strength, or really conjugate base stability. Okay, so there's this acronym that we're going to learn, ARIO. A-R-I-O. And each one of these letters stands for an important factor that affects conjugate base stability. Okay, so A stands for atom. And in particular, the size and electronegativity of an atom affect how stable that conjugate base would be, how stable it is with that net negative charge. Okay, so larger and more electronegative atoms are more stable with negative charge. All right, so let's compare, and actually, let's go ahead and say larger is actually a more important factor than electronegativity, so we're going to rank them here. Okay, so let's do an example of each here. Let's compare HCl, HI, and HBr. Okay, these are all quite good acids. All right, but if I want to rank them from the weakest to the strongest, I'm going to look at my periodic table and know that there's a big difference between the size of these atoms. Right? So first of all, again, we're really talking about our conjugate base. And really what we are asking ourselves is which one of these ions is the most stable? Okay, so we remember our periodic trends, right? Things increase in size going down the periodic table, okay? So we can actually even make a little bit of a cheat sheet for ourselves here. The larger, this is going to be important for atoms in the same column, whereas more electronegative is going to come into play for atoms in the same row. Because yes, you would have learned that things actually decrease in size going from left to right on the periodic table, but they don't change that much. Going down the periodic table, they change quite dramatically, right? So fluorine is quite a bit smaller than chlorine, quite a bit smaller than bromine, quite a bit smaller than iodine. Okay? So why would it be that a larger ion is more stable? All right, if you just think about those orbitals that house those electrons, right? When we talk about the size of an atom, the nuclei are always quite small, quite dense in the very middle. The size of an atom is made up by its electron clouds. So having an extra pair of electrons, having that net negative charge, if I'm a nice big ion, I can spread those electrons out. That's just more stable than if I'm a teeny tiny little ion and all that electric charge is packed into a little ball. Okay? So the larger it is. So if I'm going to rank these here, what's my weakest? The HCl. Followed by HBr. And then the strongest would be the hydroiodic acid. Okay, so now let's take another set of acids and see if we can't do the same thing. Okay, so now these share a row, so size isn't going to be a big factor here. All right, but this is that other one. When they share a same row, we're going to look at electronegativity. So that's going to be the deciding factor here. So what do we think? Which one's going to be happier having a negative charge? The more electronegative element or the less electronegative element? More, right? Electronegativity is this tendency to pull electrons onto yourself. These are atoms that are really sort of good at holding electron density. So more electronegative implies a stronger acid. So again, if I'm going to rank these from weakest to strongest, which one here is my weakest acid? The nitrogen one, yep, the ammonia, NH3. Okay, followed by water, and then the best acid up there would be hydrofluoric acid. Okay, so again, in our acronym ARIO, the A is for an atom, and in particular the size and the electronegativity of an atom. The larger the atom, the more stable it is holding a negative charge. So this is a factor that we're going to consider for atoms that live in the same column. And the more electronegative the atom is, the more stable it is with that negative charge. And this is a rule we'll apply for atoms in the same row. Okay. Our resonance, oh, well, that gave it away. The R stands for resonance, right? So another factor that we know leads to stability. All right, so more resonance contributors in your conjugate base implies more stability and thus a stronger acid. Okay? So let's compare two acids here. Let's compare, let's do nitrous acid and nitric acid. All right, so these are my acids. What structures am I going to compare? The conjugate bases. Oh, there's one pair here. Okay. Both of these molecules have resonance associated with them, right? So how can I tell which one's going to be the more stable of the two? The one has more resonance structures, right? So there are two contributors that I can draw here, and there are three contributors that I can draw here, right? So more resonance means more stability. Okay, so this the nitric acid NO3, HNO3 is going to be the stronger than nitrous acid HNO2. All right, and you guys sort of already intuitively applied this same logic up here, right? When we were comparing this alcohol with its OH group to this, what's called a carboxylic acid, we said that this one was stronger because that conjugate base is stabilized through resonance. Okay, so in our acronym, the R in ARIO is for resonance. All right, the I, this is for induction. All right, so induction is when you have an electronegative element just kind of nearby to the atom that's going to be holding the charge. All right, so let's compare two here. I think this might be easiest to see sort of illustrating here. Let's take this molecule, and then we have a very similar one. But now I'm going to stick this halogen right next door. Okay, so this is my acid. Everybody take a second and draw me the conjugate base. All right, so again, remember you're going to replace, sort of deprotonate this oxygen, removing that hydrogen, and in its place will just be a lone pair. Okay, so let's look at these conjugate bases real quick. Are there resonance associated with these structures? This doesn't fall into any of our resonance categories here. And in terms of the atom that's holding that negative charge, right, my A in REO, they're both oxygens. So for those first two sets, I wouldn't be able to differentiate here, okay? But this is induction. I have this electronegative element that is right next door to the atom holding that negative charge. And so it adds a little bit of stability there for having that oxygen be negatively charged. So that's what induction is a nearby large electronegative element. Actually, let's just leave it at electronegative. And that helps stabilize the negative charge. So the presence of that very electronegative fluorine next door to that oxygen with the negative charge stabilizes it through induction. So this is more stable, which again implies that this is my stronger acid.
So the fluorine, if it was a longer chain, the fluorine was like
Yeah, so we're gonna see two examples, and that's gonna be one of them. Yep. So the closer it is to that negative charge, the more it's able to stabilize it. Absolutely. Okay. So I'm gonna put up two different pairs of molecules here, and you're going to tell me which one you think is the stronger acid. Okay, all right, I'm going to put 3 down. All right, so there's 2. And the third one. Oops. Okay, so 2 different problems here, and both of them you're going to try to rank from weakest to strongest. All right, so let's label these ones A, B, and C. Which one's the weakest acid up there? B, because it's got no induction stabilization, right? There's no halogen, nice electronegative element there. And then what do we think is going to be the most acidic one up here, the strongest acid? A or C. So it's actually so electronegativity is the main factor here. Fluorine, being the most electronegative element, is actually better able to stabilize. So A is going to be our strongest. Okay, that's not to say that C is not strong at all. It's still stronger than the non-induction stabilized one. All right, but using our electronegative element stabilizing that negative charge, the fluorine is more electronegative.
So for induction, the size?
No, just the electronegativity. I backtracked there. My bad. Okay. All right, and then what about for this next set of examples here? Again, we'll label these A and B. Which one do we think is going to be the weaker of the two? A is weaker than B. B is the stronger acid. And why would that be? Just the location of that inductive group, that electronegative ion, to where that negative charge is, right? When this thing becomes its conjugate base, that negative charge is going to be sitting on that oxygen atom. The fluorine can do a better job of stabilizing that negative charge the closer it is. Okay, so our I in REO stands for induction. Okay, and our last one here, the O, is for orbital. Whoops. Yeah.
About the previous example that you had up there.
Uh-huh.
So, like on homework or an exam, if we're given the top row, are you going to ask us the strongest one based off specifically induction? Because then in the previous one for A, you said size it trumps electronegativity, so...
Yeah, so the size of the atom holding the negative charge, but in this case, they're oxygens in all of them, right? So that to be clear, your examples have to be semi-similar for you to compare them. Okay, so yes, it's going to be, these all have that same, what's called a carboxylic acid group. That's where the negative charge is going to be, right? But the question is that being stabilized through induction by a nearby element? Okay, so the O is for orbital. Okay, and this is the orbital holding that negative charge, that lone pair. Right? Remember, when acids become their conjugate bases, they're always accepting that lone pair of electrons that used to be in that acid-hydrogen bond. Okay? And so it turns out that an sp hybridized orbital is better at holding negative charge than an sp2 is better at holding negative charge than an sp3. Okay? And that's just because sp orbitals are smaller and located closer to the nucleus. All right, so they're just holding that negative charge closer to that positively charged nucleus. All right, so if we take a look at a few very simple compounds here, and this is why we wanted to go ahead and review hybridization. Okay, so let's just go through real quick. My methane, my CH4, what's the hybridization on that carbon? So this one's sp3. And what about this middle one? What about those carbons? sp2. And then finally, my last one's sp. So you can see I got very creative and put them already in order of weakest to strongest. Okay? But because this hydrogen, when this pair of electrons leaves, it joins an sp orbital, as opposed to in this one it would be an sp2 orbital. That makes this a stronger acid. Okay, now truthfully, none of these are great acids because they're carbon, which is a tiny and not very electronegative element, right? So importantly, we have our O now in our REO. The order of these letters corresponds to the order of importance of these factors. So the atom is the most important factor in determining the strength of an acid. If you're tied there, then you move down the line. Okay, is there resonance? If we're tied there, then we look at if there's induction. And then finally, if all else is equal, the deciding factor will be the orbital, right? But the orbital is not nearly as important as the atom itself. Right? A bromide is better at holding negative charge than a nitrogen regardless of the hybridization of that nitrogen. Right? So we want to look at these in order of importance. In our REO, our acronym here, the most important is that atom, that first one. And the least important, really just like the last tiebreaker, is the orbital. Okay. All right, so then in the last little bit here, let's just do some more practice problems here, okay? I guess I'll be good and do the structure. All right, so for this first one, what is the strongest acid up here? A, B, or C? C. And what's the weakest acid up here? Water. Oh my gosh. A, B, C. So the weakest. All right, and what was my deciding factor here? The size, right? They all live in the same column, right? So the question is just which is going to be the largest one. Remember, the bigger the ion, the more spread out that negative charge is. I'm going to skip this one because I'm looking at it now, realizing that it might be a little bit more complicated than I meant for it to be. So let's go on to this last one here. A or B, which one's stronger? A, because now we just got more of those nice electronegative elements to help stabilize that negative charge. Right, so my weakest is B. My strongest is A. So we see with regard to induction, right, the electronegativity of the element matters, how many of them you have, as well as how close they are to that negative charge, right? All of those are factors that will influence the ability of one of the, in this case, fluorine, to stabilize that negative charge through induction. Okay, so now I said that this one is a little bit more complicated than it sort of appears here. Which one's the stronger of the two acids? What do you think? Who thinks A? Raise your hand. Who thinks B? Raise your hand. Okay, so it is A. So my weakest is B. My stronger is A. Okay, and then what would be the reasoning? So resonance is what I think everybody's very tempted to say here, okay? But if we look at our conjugate base here, right? Remember, my conjugate base is going to have that nitrogen deprotonated. All right. So the reason why resonance isn't going to be a huge factor, there's resonance associated with the one on the left, as we said, because we have a pi bond between atoms of differing electronegativity. But let's go ahead and draw that resonance contributor. What do we notice about this nitrogen? One bond and now 3 lone pairs. It has a formal charge of -2. You are not going to see a nitrogen with a formal charge of -2. That is way too much charge concentrated on that nitrogen atom. So we have this resonance structure. This is about as crap of a resonance contributor as you could possibly have, right? I mean, it's really not going to make all that big of a difference. Okay, so I totally see why resonance was a tempting one here. But again, if we're looking at our conjugate base and we're looking at the stability here, this isn't really helping in that stability argument. Okay, but what else can we say about these nitrogens that would lead to this one being indeed the stronger of the two? The orbital, right? So now this nitrogen is sp hybridized, sp2 hybridized, whereas this one's sp3 hybridized. Okay, so you can make an argument, yeah, there's resonance. That might have a little bit of a factor here, but the bigger one here is going to be the orbital, because that resonance contributor isn't really doing much for stability. Cool, all right.